Hi everyone, I'm Yelin from Seoul National University in South Korea, and I'm honored to be here today to present our research today. The title is the Developing a Multi-Camera Analysis Methodology for People Counting in Buildings. So let's begin with the research background. The fire in the hostel of South Korea and the massive 67-story high-rise building fire in Dubai both are tragic examples where complex layouts and high occupant density severely delayed evacuations, so the damage scale was huge. The locations and timing were different, but both incidents revealed the same underlying issue. And these cases explain that why building disasters are needed to be especially managed in a specific way. For effective emergency response, there are two key information that rescue teams need to know before they arrive on site. First one is where are the occupants in the building, and the second one is how many people are in the specific location of the building. And we can know that this information by using tracking and counting occupants for each question. However, rescue teams generally estimate the occupants this data using manager statements or past rescue records. And these approaches are prone to error because they are too subjective information and just individual experience. So those inaccuracies may affect negatively to golden time life-saving operations. So it is necessary to develop automated system for accurate people counting by floor and zone in the buildings. So existing people counting systems using sensors or computer vision-based technologies occur lots of miscounts and duplicate counts when one person appears multiple times on different across various areas. And there is a lack of research on such counting error correction mechanisms. To address these challenges, it is essential to develop a detailed and practical people counting methodology through an advanced multi-camera analysis in the building. In this study, we proposed a person re-identification algorithm for additional assistance method of people counting. Person re-ID is the process of identifying and matching the same person appearing in different locations at different times. And this is an effective tool for multi-camera analysis, so it can prevent counting errors by tracking people more accurately under multiple views. Therefore, the research objective of our study is the proposal of a multi-camera analysis methodology for real-time people information management in buildings by combining a person re-identification with people counting. So these are the detailed parts of previous approaches on people counting systems. Some researchers have used the sensors for people counting, but various types of sensors were too sensitive under various environmental factors, such as temperature, humidity, or signal condition. Also, they often required huge time and cost for installation and device management. To address these limitations, people counting studies using computer vision technologies have been introduced. They utilize CCTV videos for easier data acquisition and processing. However, most of these studies used limited field of views that were hard to apply them in large spaces like the buildings, and they didn't consider detailed level of counting like zone or floor. So in the case of person re-identification researches, recently various deep learning techniques have been used to extract features of people and match each person based on the feature similarity. However, most of these studies didn't additionally consider camera network in multi-camera systems, which has led to low accuracy of the re-identification. To overcome this limitation, we proposed an advanced people matching using camera network in an easy form. So this is the framework of our study, and there are three modules in our studies. The first one is people detection and tracking, and the second one is camera network matrix mapping, and the last one is people matching and counting. So I will explain the detailed part of each module. So we applied YOLO version 8 and byte track algorithm to detect and track occupants in the building. And individuals who tracked indoors were classified into query, which is the input data of the matching model. And individuals tracked at building entrances are classified into the initial gallery data set, which is the reference data in re-identification. Also, in particular, to create the initial gallery data set, we set virtual line of interest called LOI at each building entrance. Using this line, initial gallery ID was assigned to someone who crossed the line at each entrance. So before the camera network matrix mapping, we defined 4 common facility types in the building: entrances, stair elevators, hallway, and rooms. And using these key facilities, we developed the general case of moving sequence in the building. Through identifying the locations of each facility in the experiment building, we designed the plausible movement routes by mapping camera IDs to these key locations in the building. And based on the designed movement patterns using the camera IDs, the next step is convert them into a binary matrix to express the sequential relationship between multiple cameras mathematically. In this binary matrix, a value of 0 indicates that there is not any continuous relationship between 2 cameras, while the 1 value means that there is a continuous relationship between 2 cameras. And through this matrix, the matching module can select the previous camera list of a given query that can be used as a matching gallery candidate. In the final module, among gallery candidates, the gallery ID which shows the highest feature similarity score is matched with the given query. So we trained 3 representative feature extraction model on market dataset. And as you can see in the right table, Swin Transformer version 2 showed the highest MAP in the market dataset. So we selected this model for feature extraction in this study. After this step, the similarity between a given query and gallery candidates are calculated using cosine similarity methodology, and the matching threshold was set to 0.7. Based on the matching results, we performed people counting by floor and zone of the building. To avoid miscounts in the blind spots, our counting rule remains counts in the previous zone during the blackout period, and then update the count to the next zone when the person is redetected in the other zone. So this is the result and discussion section of our study. The proposed people counting methodology is experimented in 3-story building at Seoul National University. So except closed camera during the experiment, we finally used 14 CCTV videos with non-overlapping views, 3 videos from the entrances, and 11 videos from the indoors. Also during the experiment, total of 12 individuals were entered the building, with no one exiting the building. And to generate zone-based counting results, we divided the building into 4 sections per floor based on the key facility that we defined before. So there were total 12 zones in the experiment building. And these are the performance of people detection and tracking in this study. People appeared in most of cameras were tracked in high precision, but the recall was relatively low because some individuals appeared in dark areas of the building, or they were captured from a distance, so tracking in these cases makes some failures. And the image below shows an example of LOIs drawn at 3 entrances of the experiment building, and the results of assigning initial gallery IDs to people who passes this line. The people matching module successfully matched 19 cases out of 22 actual ID matching cases. This video is the result of people re-ID across all camera systems, and this proves that the proposed system allows continuous occupant monitoring across non-overlapping zones through re-ID. However, we observed some mismatched cases, like the example in the incorrect match. Some cases when individuals lacked clearly distinguishable features such as wearing dark clothing, the similarity scores between candidates were very close, which led to incorrect matches. And this is the result of people counting in the classified zone of the building. On average, the system achieved a MAE of 0.094. In the graph on the right, solid line, the line is the experimental result, and the dotted line is the ground truth. Also, we visualized the location of people at specific time points on a 2D plan of the building. And as shown in the graph, the gap between the ground truth and the experimental results tends to increase slightly over time. This is partly due to our counting rule, which maintains counts in the previous zone during the blackout period. While this approach helps prevent immediate miscounts, but small error can gradually accumulate over time. And this is the final output of the people counting per zone in the building. And this video shows that the proposed people counting system can update real-time counting results in each zone using spatial and re-ID information. So like this one. And based on the analysis of the results, in most zones, accurate people matching result in each zone improved counting precision by mitigating the counting errors. So our methodology has achieved 10% accuracy increase and 0.1 MA reduction compared to prior studies of people counting. However, there were some special scenarios that didn't follow the general trend. In the case 1, there was some error in matching, but the counting accuracy was high due to associating alternative ID correctly in the count. On the other hand, in the case 2, the matching accuracy was high, but counting shows the high error rate due to failure of re-ID in the other zone. In conclusion, determining the number of occupants in specific building zones before a disaster is crucial for effective rescue operations. To address this, we proposed a new multi-camera analysis methodology for real-time people counting in buildings with re-ID technology based on camera network metrics. So our approach enabled highly accurate people counting in non-overlapping areas by correcting errors through a matching algorithm. So the proposed method can be a valuable tool for efficient decision-making during building disaster response. Thank you for, these are the reference, and thank you for listening to my presentation.